There is a comet just past Jupiter that has been spontaneously exploding for years. Not slowly leaking gas, not gently venting, exploding, up to 30 times per year. In 2024, it erupted 4 times in a 48-hour window and grew nearly 300 times brighter in the span of a few hours. Scientists have no reliable way to predict when it will go off next. And that is just one of dozens of mysteries currently being unraveled by the most powerful space observatory ever built. Before we continue, if this kind of content sparks your curiosity, subscribe, because the deeper we go, the more surprising it gets, and most people never hear about what you're about to see next. The James Webb Space Telescope has now been operational for several years, and what it is returning to Earth is not what we expected. Not just in the sense that the images are beautiful, though they are, but in the sense that discovery after discovery is forcing scientists to reconsider assumptions that have stood for decades. Models that described how the first stars formed, how galaxies grew, how black holes came to exist, and how planetary systems are assembled are all being challenged by what this telescope is seeing. Some of those challenges are subtle, others are profound enough to require a rethinking of the fundamental cosmological models that underpin modern astrophysics. This is the story of what the James Webb Space Telescope has found. From objects in our own solar system to galaxies that existed less than 300 million years after the Big Bang, and the cosmic mysteries those findings are forcing us to confront. To understand why this telescope matters so much, you need to understand the problem it was built to solve. When we look at the universe with visible light, we are limited in 2 fundamental ways. The first is dust. The universe is not a clean vacuum. It is threaded with vast molecular clouds and nebulae made of gas and microscopic particles of silicate and carbon. These clouds scatter and absorb visible light, making entire regions of the cosmos effectively invisible to optical telescopes. Stellar nurseries, the places where stars and planets are actively being born, are among the most heavily obscured regions in existence. For most of the history of astronomy, we could only observe the shells of these regions, never the interior. The second limitation is more fundamental. The universe is expanding. As light travels across billions of light years of space, the very fabric of space stretches, and that stretching pulls the wavelength of light along with it. By the time light from the very earliest galaxies reaches us, it has been shifted so far toward longer wavelengths that it has left the visible spectrum entirely and moved into the infrared. A telescope that can only see visible light cannot see these galaxies at all, no matter how large or powerful it is. Infrared light solves both of these problems. It passes through dust more easily than visible light, and it is precisely the wavelength that the most distant and ancient galaxies emit. This is what the James Webb Space Telescope was built to capture. Launched on the 25th of December, 2021, and brought to full operation in July of 2022, it carries a primary mirror nearly 6.5 meters across, made of 18 gold-coated hexagonal segments of beryllium. It is stationed at the second Lagrange point, a gravitationally stable location approximately 1.5 million kilometers from Earth in the direction away from the Sun. And as of 2025, it has already completed more than 860 scientific programs and collected nearly 550 terabytes of data. That is more data than the Hubble Space Telescope accumulated across 35 years of operation. What that data is revealing will take decades to fully process, but already the findings are staggering. Let us start close to home at the edge of our own solar system with Neptune. Neptune is usually recognized for its deep blue color, a result of methane in its atmosphere absorbing red wavelengths of sunlight and reflecting the remaining blue. But viewed through the James Webb Space Telescope's infrared detectors, Neptune looks entirely different. Because methane absorbs nearly all infrared light, very little is reflected back, and the planet itself appears dark. What that darkness reveals, however, is remarkable. Without the planet's usual brightness dominating the image, the subtle and faint glow of Neptune's ring system stands out in extraordinary detail. Dusty rings that were previously difficult to observe are now clearly visible, along with ring arcs and structural features we had not seen before. 14 of Neptune's known moons appear in the same field of view. Scientists are still analyzing these images to understand the precise composition and structure of the rings, and what they reveal about the dynamics of the outer solar system. These are the clearest observations of Neptune's ring system ever taken. and they were a direct result of the telescope's infrared sensitivity, turning a limitation of the planet's atmosphere into an observational advantage. But Neptune was a warm-up. James Webb's attention in the outer solar system has recently turned to something far more unusual. On the 6th of August, 2025, the telescope trained its near-infrared spectrograph on Comet 3 I Atlas. This was not an ordinary comet. It was an interstellar visitor, an object that did not form in our solar system but arrived from another star system entirely. A small number of such objects have been detected passing through our solar system in recent years, and each one represents a rare opportunity to directly sample the chemistry of a planetary system that formed around a different star. What James Webb found in Comet 3 I Atlas was a composition unusually rich in carbon dioxide and water vapor, with a ratio between the two among the highest ever detected in any comet. This ratio is not random. It reflects the temperature conditions present where the comet originally formed, in a region of its home star's protoplanetary disk, cold enough for carbon dioxide ice to naturally condense. By directly measuring the chemistry of an interstellar body, James Webb has provided evidence that the basic molecular building blocks of planetary systems, including the chemistry that ultimately gave rise to life on Earth, are not unique to our solar system. The same elements, the same compounds, the same chemical processes that shaped our world appear to be reproduced across the galaxy. The universe is not experimenting with life in one place. It appears to be running the same experiment in many places at once. Closer to our own solar system, James Webb has also changed what we know about the immediate stellar neighborhood. Just over 4 light-years away lies the Alpha Centauri system, a trio of stars consisting of 2 Sun-like companions, Alpha Centauri A and Alpha Centauri B, and the red dwarf Proxima Centauri. For decades, astronomers suspected that planets might orbit the 2 larger stars, but the intense and overlapping glare of the 2 Sun-like stars made direct detection impossible. You cannot look for faint planets next to 2 stars that are effectively blinding every instrument pointed at them. James Webb changed this using its mid-infrared instrument and an internal coronagraph, a device that physically blocks the light of a target star so that dimmer objects nearby become visible. The analogy is simple. It works similarly to the way a car's sun visor blocks direct sunlight so that you can see the road ahead. With the blinding starlight removed, the telescope detected a faint point of light that represents the closest exoplanet candidate ever to be directly imaged. Analysis suggests it is a potential Saturn mass gas giant orbiting Alpha Centauri A, and orbital simulations indicate its path may carry it through the star's habitable zone. The gas giant itself would not be a candidate for life as we understand it, but a gas giant in a habitable zone can have moons, and those moons could be worlds with stable temperatures, atmospheres, and liquid water. The discovery confirms that planetary formation has occurred around our nearest stellar neighbor and opens the question of what smaller worlds might yet be waiting to be found in that system. These exoplanet discoveries are connected to a deeper question. How do planets actually form? This is a process that James Webb is now able to observe in unprecedented detail. The pillars of creation in the Eagle Nebula, 6,500 light-years away, are one of the most iconic images in the history of astronomy. The original Hubble images, taken in 1995 and updated in 2014, showed towering columns of gas and dust that have become symbols of cosmic creation. But what Hubble saw was the exterior of these structures. The dense dust that makes them so dramatic in visible light is precisely what prevented a deeper look. James Webb sees through that dust. Its near-infrared camera view of the same pillars reveals thousands of previously unseen stars, including very young protostars still embedded deep within the dusty columns. These infant stars appear as bright red points of light, their glow coming from energetic hydrogen molecules excited by plasma jets and shock waves radiating outward from the newborn stars. The tops of the pillars are not quiet. They are pulsing with the chaotic energy of stellar birth happening right now, in real time. A similar view has been captured at the Cosmic Cliffs, the turbulent edge of the Carina Nebula, 7,600 light-years away. Here, James Webb's near-infrared camera has captured the fine structure of a gaseous landscape being actively eroded by intense ultraviolet radiation and stellar winds pouring off massive young stars above it. What previously looked like a serene and beautiful panorama in visible light is revealed in infrared to be a battlefield of competing energies, where the material that will form the next generation of stars is being shaped by the stars that already exist. These observations matter not just for their beauty, but for what they tell us about the physics of star formation. Prior to James Webb, our understanding of stellar nurseries was largely based on indirect observation and theoretical modeling. Now we can see inside these regions directly and test those models against real data. And what James Webb is finding is that stellar births are violent, explosive events. In a region called Sharpless 2284, approximately 15,000 light-years away on the outer edge of the Milky Way, James Webb found something extraordinary, a massive protostar in the process of forming, with a mass estimated at roughly 10 times that of our Sun. Surrounding it, the telescope detected a pair of enormous jets of gas and radiation, known as a bipolar outflow. These jets form when superheated in falling gas is simultaneously channeled by the protostar's magnetic field and blasted back outward into space along the star's rotational axis. They represent a star announcing its own birth. What makes this particular discovery remarkable is the scale of these jets. They span 8 light-years. To put that in perspective, the entire distance from our Sun to the Alpha Centauri system is just over 4 light-years. These jets are nearly twice that distance. They are blasting outward at hundreds of kilometers per second, acting as an enormous cosmic plow that sweeps away the surrounding molecular cloud and carves out a cleared region within which the star will eventually settle. The symmetrical and stable nature of the outflow provides evidence for what is known as the core accretion model of massive star formation, where material falls inward through an ordered disk and magnetic fields channel the excess outward. What makes the location of this discovery particularly significant is its position on the far outer edge of the galaxy, where the concentration of heavy elements is extremely low. Stars in this region contain far fewer elements beyond hydrogen and helium than stars in the galaxy's inner regions. This metal-poor environment closely mirrors the conditions that existed across the entire early universe, when only the very first generation of stars had begun to produce heavier elements through nuclear fusion. By observing massive star formation, a ring of material surrounding a massive young exoplanet, these structures are the sites where moons form. The disk around CTHB's planet is the equivalent of what existed around the early Jupiter, when that giant planet was generating its system of moons, including Europa, Ganymede, and the others. By directly imaging and analyzing this disk with its mid-infrared instrument, James Webb delivered the first measurements of its chemical and physical properties. What the telescope found was striking. The disk is rich in carbon-containing organic molecules, including acetylene and benzene, but the disk surrounding the host star itself contains water and very little carbon. The chemistry of the moon-forming disk around the planet is fundamentally different from the chemistry of the planet-forming disk around the star. This chemical contrast, observed in a system only 2 million years into its formation, allows scientists to directly compare the ingredients for moon formation in an alien system against our own solar system's 4-billion-year-old history. The universe builds moons using different recipes in different places, and James Webb is beginning to document those recipes. On a larger scale, James Webb has given us our most detailed view of entire galaxies in the process of building themselves. In 2024, the telescope focused on 19 nearby spiral galaxies and produced images that are difficult to fully absorb. These are not just photographs, they are maps of the machinery of cosmic creation. In a galaxy like NGC 628, also known as the Phantom Galaxy, located approximately 32 million light-years away, the infrared view is a revelation. The older established stars clustered in the galaxy's core appear in blue. Threading through the spiral arms in vivid red and orange are the lanes of glowing gas and dust from which new stars are being born. Within those lanes, the brightest red concentrations mark individual stars or clusters of stars still encased within their natal dust, not yet fully formed. And woven throughout are giant spherical shells, massive cavities carved into the gas by the shock waves of ancient supernovae. Each bubble marks the death of a star massive enough to explode, and in that explosion, it cleared the way for the next generation. Studying these patterns across 19 different galaxies simultaneously allows scientists to look for universal principles of galactic structure and star formation. to understand what mechanisms govern the cycle by which galaxies build themselves up over cosmic time. But fully formed galaxies represent only one piece of the puzzle. The deeper question is how the very first galaxies came to exist. For that, James Webb has had to look to the very edge of the observable universe. Even with the most sensitive infrared detectors ever built, there is a fundamental limit to how far back in time we can observe using light alone. The earliest light in the universe was released a few 100,000 years after the Big Bang, when the universe first cooled enough to become transparent. Before that moment, the universe was an opaque plasma and no light could travel through it. But physics offers an additional tool for seeing distant objects, one that does not require the object's light to travel directly to us. Gravitational lensing is the bending of light by mass. A galaxy cluster is so enormously massive that its gravity warps the geometry of space around it. Light from distant galaxies behind the cluster follows the curved geometry of that warped space. And to an observer on the other side, the light appears to have been bent and in some cases amplified. The galaxy cluster effectively acts as a magnifying lens, allowing James Webb to see objects that would otherwise be too faint to detect. Using a cluster called RxJ 2129, located 3.2 billion light-years away, James Webb captured a distant supernova explosion lying behind the cluster. But the telescope did not see the event once. It saw it multiple times. The light from the explosion took different paths around the cluster's warped space-time, arriving at slightly different times. The same supernova appeared as several separate images, each an echo from a slightly different moment in the event's history. By measuring the time delays between those echoes, astronomers can precisely calculate the geometry of the space between us and the source, providing an independent measurement of the universe's expansion rate. This is directly relevant to one of the most persistent and puzzling disagreements in modern cosmology, a discrepancy in measurements of how fast the universe is expanding that has resisted resolution for years. James Webb's gravitational lensing observations may eventually provide the data needed to settle this debate. At the very outermost limit of what James Webb can observe, the telescope has begun to reveal galaxies from the cosmic dawn, the period within the first several 100 million years of the universe's existence. And what it has found there has genuinely surprised the scientific community. Working with its near-infrared camera and spectroscopic instruments as part of the JWST survey, the telescope has confirmed the existence of galaxies far brighter, far more massive, and far more structurally complex than theoretical models predicted for that early epoch. One galaxy, now designated JWST 14-0, has been confirmed to exist only 300 million years after the Big Bang. Another, catalogued as Z14 and spotted in May of 2025, is approximately 10 million years older. These are among the earliest known galaxies in the observable universe. The problem is that they should not exist in their current form. The standard cosmological model, known as lambda cold dark matter, predicts that galaxies at this epoch should be small, dim, and composed only of the simplest and most primitive early stars, only just beginning to assemble. Instead, JWST 14-0 is too large, too bright, and too mature. For a galaxy to have grown to this size in only 300 million years, the early universe would have had to be forming stars at a rate far faster and far more efficiently than any current model allows. The very existence of this galaxy forces a confrontation with the foundations of modern cosmological theory. Several explanations are being explored. One is that stellar feedback, the process by which newly formed stars heat and disrupt the surrounding gas and slow down further star formation, was less effective in the early universe than models assume. Another is that dark matter behaved differently at early times, providing gravitational wells that concentrated gas faster than expected. A third possibility, more speculative but grounded in theoretical physics, involves what some researchers have called dark stars. The idea of dark stars was first proposed in 2007 by cosmologists Catherine Fries, Paolo Gondolo, and Douglas Spolia. These hypothetical objects would not be powered by nuclear fusion the way ordinary stars are. Instead, their energy source would be the annihilation of dark matter particles within their cores. Dark matter is the invisible material that accounts for roughly 85% of all the matter in the universe. Its exact nature is unknown, but leading theoretical models describe it as consisting of particles that can mutually annihilate when they collide, releasing energy in the process. If dark matter density was high enough in the early universe, and if it collected in the cores of collapsing gas clouds, the energy released by annihilation could have been sufficient to power stellar objects, orders of magnitude larger than any normal star. These dark stars could have grown to masses millions of times that of our Sun, and because they would have been powered by annihilation rather than fusion, they would have been cool and long-lived, producing the exact kind of infrared emission that James Webb is designed to detect. It is possible, though not yet confirmed, that some of the extreme sources James Webb is observing at the cosmic dawn are not galaxies at all, but individual dark stars. This would directly connect the telescope's most distant observations to the most poorly understood component of the universe. Whether through dark stars, revised star formation efficiency, or some other mechanism not yet identified, the fact that these early massive galaxies exist at all indicates that something in our current picture of the early universe is incomplete. James Webb has not just taken pictures, it has raised fundamental questions. Now let us return to the solar system, to the object that opened this story, the comet that will not stop exploding. Centaur 29P was discovered in 1927 by two astronomers at Hamburg Observatory, Arnold Schwassmann and Arno Arthur Wachmann, while comparing photographic plates of the night sky. It was initially classified as a short-period comet, but was later reclassified as a centaur, a designation given to solar system bodies orbiting between Jupiter and Neptune that display characteristics of both comets and asteroids. The name centaur is a deliberate reference to the mythological hybrid creature, half human and half horse. These objects are compositionally hybrid as well, combining rocky and icy properties that reflect their origins in the distant Kuiper belt. Centaur 29P has two properties that set it apart from most centaurs. The first is its orbit. Most centaurs move on elliptical paths that vary significantly in their distance from the Sun, meaning their exposure to solar radiation changes dramatically over the course of each orbit. Centaur 29P, by contrast, follows a nearly perfect circle at a distance of roughly 6 astronomical units from the Sun, approximately 6 times the Earth-Sun distance. This means it receives essentially constant solar radiation throughout its orbit. It should behave predictably. The second distinguishing feature is its size. At 60 kilometers in diameter, it is wider than 96% of all known centaurs. This is not a small object. It is a substantial icy body with significant mass, and it explodes, on average, approximately 30 times per year, making it the second most active body in the solar system after Io, one of Jupiter's volcanic moons. In 2024, it erupted 4 times within a 48-hour period, brightening by nearly 300 times. 2 years earlier, it ejected more than 1 million tons of material into space faster than the speed of sound. In September 2021, it experienced its largest outburst in 40 years when it erupted 5 times consecutively. And 40% of these outbursts occur without any detectable precursor or predictable pattern. The physical mechanism behind these eruptions is understood in broad terms. Centaur 29P is a cryovolcanic object, meaning it contains volatile ices beneath its surface that can suddenly sublimate and erupt outward under pressure. Its interior is composed primarily of carbon dioxide, carbon monoxide, nitrogen, and water ice. Over time, radiation from the Sun progressively weakens the outer crust. As the internal pressure of sublimating gases builds, the crust eventually fractures, releasing explosive jets of cryomagma, a mixture of frozen water, ammonia, salts, and volatile gases. Because the centaur's gravity is significant, much of the ejected material does not escape into space but falls back onto the surface, potentially triggering the follow-on eruptions that frequently occur 5 to 7 days after a major outburst. What is not understood is why the eruptions occur when they do and with the intensity they achieve. The nearly circular orbit eliminates the most obvious explanation available for other active comets, which is that increasing solar proximity drives increasing activity. Some researchers have noted a loose periodicity to the eruptions, suggesting a possible relationship to the Centaur's slow rotation period of 57 days. Outbursts appear somewhat more frequent on cycles of 52 to 60 days, with secondary periodicities at 30 and 90 days. But these patterns are far from regular enough to serve as reliable predictors. In April 2023, scientists managed to predict a minor outburst by observing a significant dimming of the comet's coma, which they interpreted as a buildup of internal pressure. Their prediction was correct. The comet erupted that same day. It was the first successful prediction of a Centaur 29P outburst ever recorded. The brief sense of progress was encouraging, but the larger mystery remained. Then James Webb provided a new piece of the puzzle. Prior to the James Webb observations, scientists knew that carbon monoxide was present around Centaur 29P in high concentrations, and carbon monoxide had been assumed to be the primary driver of the outbursts. Carbon monoxide is an extremely volatile compound. Pure carbon monoxide ice can sublimate at temperatures as low as 25 Kelvin, which is 248 degrees Celsius below zero. If it were present near the surface of the Centaur, it would have escaped long ago. To persist, it must be stored deeper within the object, preserved somehow against the temperature gradient between the surface and the interior. James Webb's near-infrared spectrograph revealed something that radio wavelength observations had missed. What had appeared to be a single jet of carbon monoxide was actually two distinct jets, one pointing toward Earth and one directed northward. And the telescope also detected two additional jets of carbon dioxide, one from the northern face of the Centaur and one from the south. This was the first confirmed detection of carbon dioxide on Centaur 29P. The difference in spatial distribution between the carbon monoxide and carbon dioxide jets strongly suggests the Centaur may not be a single unified object at all, but rather several distinct bodies that have aggregated together over time, each with its own composition and its own separate regions of activity. This would explain some of the irregularity in the outbursts. Different regions with different compositions would respond to changing conditions differently, producing eruptions from multiple sources that overlap, interact, and appear chaotic when viewed from the outside. One leading hypothesis for the source of the unusually high carbon monoxide levels involves a form of water ice almost entirely absent from everyday experience on Earth. Amorphous ice is water ice that lacks the crystalline molecular structure of the ice we are familiar with. Where crystalline ice has an ordered, regular arrangement of water molecules, amorphous ice is disordered and loosely packed. This lower density structure creates gaps and pores that can physically trap gas molecules within the ice matrix. On Earth, amorphous ice is only stable at temperatures below -140 degrees Celsius and reverts almost instantly to crystalline form at warmer temperatures. But in the outer solar system, temperatures are cold enough to preserve amorphous ice for millions of years. The conversion from amorphous to crystalline ice occurs spontaneously as temperature rises above 77 Kelvin. As the ice converts, it becomes more dense and releases whatever gases are trapped within it. For Centaur 29P, which originated in the Kuiper belt at temperatures between 30 and 40 Kelvin, its ice would have formed in the amorphous state. As it migrated inward over roughly 10 million years to its current position at 6 astronomical units from the Sun, its surface temperature rose to approximately 115 Kelvin, above the threshold for amorphous to crystalline conversion. Here is where the Centaur's unusual size becomes critically important. Small Centaurs, measuring between 1 and 6 kilometers across, can complete the full conversion of their amorphous ice to crystalline ice in a period of between 100,000 and 6 million years after reaching their current orbital position. By the time they are in a similar location to Centaur 29P, they are essentially fully converted. Their trapped gases have been released, and their behavior is relatively predictable. Centaur 29P, at 60 kilometers in diameter, would require between 60 and 100 million years to complete the same conversion throughout its entire volume. Based on current calculations, it may have converted only 50 to 65% of its amorphous ice so far. That means a substantial reservoir of trapped gas is still locked within the Centaur's interior, slowly being released as the conversion front progresses inward. As the amorphous ice converts to the denser crystalline form, the overall volume of the nucleus shrinks. This volumetric reduction can induce structural stress throughout the interior, potentially triggering cave-ins, internal collapses, and landslide events along the boundaries between converted and unconverted zones. These structural failures may be what drives the Centaur's erratic and explosive outbursts, as newly exposed amorphous ice suddenly undergoes rapid conversion and releases its trapped gases. But this model, though elegant, leaves questions unanswered. It does not fully explain how pressure can build fast enough to trigger multiple high-intensity eruptions within a 48-hour period, or why some outbursts are many times more powerful than others. The detailed mechanics of how Centaur 29P goes from stable to explosive on such short timescales remain unclear. This is not unusual. Science rarely answers all questions at once. What James Webb has done for Centaur 29P is provide the most detailed compositional picture we have ever had of this object, revealing structure and complexity that could not be seen before. The presence of multiple gas jets from different directions, the first confirmed detection of carbon dioxide, the suggestion that the object may be a composite of multiple bodies, these are all pieces of a puzzle that researchers are still assembling, and puzzles are not limited to the solar system. The discovery of those unexpectedly massive and bright early galaxies has brought renewed attention to one of the oldest unsolved problems in astrophysics. How did the supermassive black holes at the cores of galaxies come to exist? Today, we know that almost every large galaxy in the universe contains a supermassive black hole at its center. The black hole at the heart of the Milky Way, known as Sagittarius A*, has a mass approximately 4 million times that of our Sun. The black holes at the centers of some other galaxies dwarf even this. Masses of hundreds of millions to billions of solar masses have been measured, and these are not especially rare. The universe is full of them. The problem is one of origin. The only way we have traditionally understood how black holes form is through the death of very massive stars. A star with a mass greater than roughly 20 times that of our Sun can, at the end of its life, collapse inward in a supernova explosion with enough force to overcome the pressure of its own atomic structure, creating an object so dense that not even light can escape its gravity. This is a stellar black hole. These objects typically have masses ranging from a few times the mass of the Sun up to perhaps a few hundred solar masses. At the upper limit, there is no known mechanism by which a stellar black hole can grow from a few solar masses to millions or billions of solar masses. In the time available in the early universe, at least not without consuming matter at rates that violate the physical limits on how quickly a black hole can accrete material. Those limits exist because as a black hole eats, the infalling matter heats up and radiates energy outward. If a black hole accretes too fast, the radiation pressure from that heating process pushes back and interrupts the accretion. There is a theoretical maximum rate, known as the Eddington limit, beyond which accretion cannot proceed under normal conditions. The discovery of supermassive black holes in galaxies that existed only 500 million years after the Big Bang made this problem acute. James Webb has confirmed the existence of these little red dots, as researchers have informally called them, dense compact objects harboring enormous black holes at the edge of the observable universe. There has simply not been enough time under conventional models for stellar black holes to have grown to these sizes, not unless they formed very close to their final mass to begin with. This is where the idea of primordial black holes becomes relevant. In the fraction of a second after the Big Bang, the universe was an unimaginably hot and dense plasma. The distribution of matter in this plasma was not perfectly uniform. There were regions of slightly higher density and regions of slightly lower density, random fluctuations in the fabric of the newborn cosmos. In regions where those density fluctuations were large enough, the theory of primordial black holes proposes that the density could have exceeded the threshold needed to form a black hole directly from the primordial matter itself, without any star ever forming first. This idea was first proposed in 1966 by physicists Yakov Zeldovich and Igor Novikov. Under certain conditions, the theory allows for the formation of primordial black holes with masses enormously greater than those produced by stellar collapse, potentially 100,000 times the mass of our Sun or more. If such objects formed in the early universe, they would have had billions of years to continue accumulating mass, potentially explaining the supermassive black holes we observe today, without requiring impossible accretion, rates from stellar mass progenitors. But primordial black holes could also have formed with very small masses. The same density fluctuations that could produce giants could also produce tiny black holes, objects with masses comparable to an asteroid or a mountain, compressed into volumes far smaller than an atomic nucleus. These are what some researchers have informally referred to as black hole rhinos, named for the fact that the most compact of these hypothetical objects could have a mass comparable to that of an adult rhinoceros while being smaller than a single proton. Until recently, this was largely theoretical. There was no direct observational evidence that black holes formed in any way other than through stellar collapse. But in July 2025, NASA announced that James Webb had observed something difficult to explain within any standard framework. The telescope imaged two early disk galaxies in the process of merging, and located between them, not at the center of either galaxy, but positioned in the space between the two, was a supermassive black hole. This black hole had not been ejected from either galaxy. Both galaxies already possessed their own supermassive black holes at their centers. This third black hole appeared to have formed in situ, in open space, without a host galaxy. The team analyzing the discovery proposed that it had formed through the direct gravitational collapse of a dense gas cloud, without any stellar intermediate. A second data point came from James Webb's observation of an object designated QSO-1, a supermassive black hole inhabiting an unusually small galaxy. Spectral analysis of this system found extremely low concentrations of heavy elements, defined in astronomy as anything beyond hydrogen and helium. The galaxy's oxygen abundance was less than 1% of what we observe. In the Milky Way, stars produce heavy elements in their interiors through nuclear fusion and distribute those elements into the surrounding galaxy when they die. A galaxy with almost no heavy elements is a galaxy where very little stellar generation has occurred. The near absence of these elements in QSO-1's galaxy suggests that the supermassive black hole within it had not arisen from generations of stellar evolution. It was there before the stars had time to significantly enrich the galaxy's chemistry. This is circumstantial but compelling evidence that at least some supermassive black holes did not form from stars at all. Taken together, these two observations lend significant weight to the primordial black hole hypothesis, or at minimum to the direct collapse hypothesis, which shares the core implication: black holes can form without stars. And if the early universe was capable of producing very large primordial black holes, it was almost certainly capable of producing very small ones too. This is where the story takes a turn that extends beyond cosmology into a question with practical, if extraordinarily long-term, implications. The universe contains far more gravitational influence than can be accounted for by all the visible matter within it. Astronomers have known for decades that galaxies rotate too fast for their observed mass to hold them together. That galaxy clusters contain more gravitational binding energy than their visible stars and gas can provide, and that the large-scale structure of the cosmos is distributed in a pattern that requires significantly more mass than we can see. This unseen mass, which appears to constitute approximately 85% of all matter in the universe, is called dark matter. We do not know what dark matter is. We have never directly detected a dark matter particle. We observe its gravitational effects everywhere, but have not yet identified its physical nature. Numerous candidates have been proposed and searched for, including massive particles that interact only through gravity and the weak nuclear force, sterile neutrinos, axions, and others. None has been definitively detected. Black holes, particularly small ones with no surrounding accretion disk of glowing material to announce their presence, are massive and essentially invisible. They would be extraordinarily difficult to detect unless they happen to pass directly between us and a background light source, producing a brief gravitational lensing event. If large populations of small primordial black holes formed in the early universe, they could in principle account for some or all of the dark matter that models require. Researchers have investigated this possibility and found that objects above a certain mass threshold would be detectable, either through gravitational effects on visible stars or through lensing events. And observations rule out large compact objects in the mass range of stellar black holes surrounding the Milky Way as a significant dark matter component. The galaxy would be a chaotic place if dense massive objects were circling it in abundance. Stars would be frequently deflected, lensing events would be common, and the overall dynamics of the galaxy would be measurably disrupted. We do not observe these effects, but small primordial black holes, the black hole rhinos, present a different situation. Their mass is low enough that their gravitational influence on individual stars would be subtle, and their lensing signatures would be extremely brief and difficult to distinguish from other transient events. There is currently no observational evidence that rules out a population of small primordial black holes as a component of dark matter. There was one argument that seemed to close this door. In 1974, Stephen Hawking proposed that black holes are not perfectly black. Through a quantum mechanical process, He argued that pairs of particles spontaneously form at the boundary of a black hole's event horizon, with one particle falling in and the other escaping as radiation. This process, known as Hawking radiation, causes a black hole to very slowly lose mass over time. The smaller the black hole, the faster it radiates and the shorter its lifetime. For black hole rhinos, the estimated lifetime under standard Hawking radiation calculations would be shorter than the current age of the universe. They should have evaporated by now. But in April 2024, a study published in the monthly notices of the Royal Astronomical Society found that at the scale of very small black holes, the dynamics of Hawking radiation may change considerably. The rate of evaporation, according to this research, might slow dramatically as the black hole approaches very small masses, potentially stopping entirely before the black hole fully disappears. If this is correct, then black hole rhinos might not evaporate. They might instead shrink to some minimum stable size and persist indefinitely, which would mean they could still be out there, circling in the dark halo surrounding our galaxy in enormous numbers, invisible, undetected, and essentially impossible to find without the most indirect and painstaking observations. Consider the implication. The dark matter that makes up the vast majority of all matter in the universe, the invisible scaffolding that shaped how every galaxy and galaxy cluster formed, could be composed entirely or partially of objects each no larger than a proton, but with the mass of a rhinoceros. Millions or billions of them distributed throughout the space surrounding our galaxy, passing through the solar system, potentially passing through Earth on rare occasions, moving through solid rock without leaving any macroscopic trace because their gravitational influence at such small scales, while theoretically calculable, is too small to directly detect with any instrument we currently possess. And if we ever attempted to leave the Milky Way and travel toward another galaxy, we would have to pass through a region where these objects, if they exist, would be most densely concentrated. The gravitational halo that extends far beyond the visible disk of the galaxy. A black hole with the mass of a rhinoceros, moving at typical dark matter velocities, encountering a spacecraft would not produce a slow cinematic destruction. The encounter would be nearly instantaneous, and the outcome would be structural failure of whatever material the black hole passed through. This is speculative. The primordial black hole hypothesis is not confirmed. The Hawking radiation slowdown is not confirmed. The idea that these objects constitute a significant fraction of dark matter is not confirmed. But it is not ruled out either. And the recent James Webb observations of anomalous supermassive black holes and metal-poor galaxies have moved this hypothesis from the fringe into the realm of active scientific investigation. What James Webb has done across all of these observations is what the best scientific instruments always do. It has taken questions that seem settled and revealed unexpected complexity. It has opened doors into regions of physics and cosmology that were previously inaccessible. It has simultaneously answered questions and generated new ones. In the years ahead, the telescope will continue its survey of the early universe, accumulating data on the most distant and ancient galaxies, refining measurements of the universe's expansion rate, imaging more exoplanets, and extending our detailed inventory of solar system objects. Its operational lifetime, based on the fuel reserves available for station keeping at the Lagrange point, is estimated to extend well beyond 20 years from its launch, meaning there are decades of discoveries ahead. The questions left open by its current findings will drive observational astronomy for years to come. How did those unexpectedly massive early galaxies form? What is the nature of the anomalous supermassive black holes found in the spaces between merging galaxies? Do primordial black holes exist? And if so, do they play a role in the dark matter problem? What are the precise mechanisms driving the eruptions of Centaur 29P? And what does the detection of multiple gas jets tell us about the internal structure of cryovolcanic objects? Does the Alpha Centauri system harbor smaller terrestrial planets beyond the gas giant candidate now in view? Every one of these questions is grounded in real observations. Every one of them has the potential to reshape our understanding of the universe in ways we cannot fully anticipate. That is what makes this moment in astronomy so genuinely extraordinary. Not the beauty of the images, though they are beautiful, not the scale of the discoveries, though it is immense, but the fact that a single instrument, built and launched within living memory, is producing findings that will occupy scientists for generations. The James Webb Space Telescope did not just open a new window on the universe. It revealed that the universe we thought we knew had been keeping far more of itself hidden than we realized. If you found this journey through the cosmos worthwhile, consider subscribing and leaving a like. There is much more to explore, and the universe is not slowing down its revelations. The next discovery could arrive any day. The story of the James Webb Space Telescope does not begin in space. It begins with a problem that astronomers had been living with for decades, one that had become more frustrating with each passing year as technology improved, but the fundamental barrier remained unchanged. Every telescope ever built to study the cosmos in visible light, from Galileo's original instrument pointed at the moons of Jupiter to the magnificent Hubble Space Telescope, shared the same limitation. They could only see what light would show them. And light, it turns out, is a deeply incomplete messenger. Light travels at approximately 299 million meters per second in a vacuum. Nothing in the universe moves faster, but light can be absorbed. It can be scattered. It can be shifted in frequency by the motion of its source or by the expansion of the space it travels through. And when any of these things happen, the information that light carries is altered or lost. For astronomers trying to understand the most distant regions of the cosmos, this is not a minor inconvenience. It is a fundamental barrier to knowledge. The cosmic dust problem had been recognized since the early 20th century, when astronomers began to notice that the density of stars as observed from Earth decreased markedly in certain directions, not because fewer stars existed there, but because clouds of interstellar material were blocking the light. These molecular clouds, composed of hydrogen, helium, and traces of heavier elements in both gaseous and solid particulate form, are the same environments in which new stars are born. The collapse of these clouds under their own gravity initiates the formation of protostars. The very dust and gas that blocks our view of stellar nurseries is the material from which stars are made. Visible light cannot penetrate these clouds effectively. The dust particles scatter and absorb photons in the wavelength range that human eyes and instruments designed to mimic them are sensitive to. To see inside a molecular cloud, you need radiation at longer wavelengths that can slip through the gaps in the dust structure without being efficiently scattered. Infrared light fits this requirement. Radio waves fit it even better. And this is why radio telescopes, beginning in the mid-20th century, provided some of the first insights into the internal structure of nebulae and star-forming regions that optical telescopes simply could not access. But radio observations have their own limitations. The angular resolution of a telescope, its ability to distinguish fine spatial detail, scales inversely with wavelength. The longer the wavelength, the lower the resolution for a given mirror or dish size. Radio observations can tell us about the presence of gas and the broad structure of clouds, but they cannot produce the kind of detailed images that allow astronomers to study the dynamics of individual protostars, the fine structure of accretion disks, or the characteristics of planets around other stars. Infrared sights in a useful middle ground. It is long enough in wavelength to penetrate most dust clouds without significant absorption, but short enough that a mirror of reasonable size can provide good angular resolution. The James Webb Space Telescope's primary mirror, at 6.5 meters across, provides infrared angular resolution comparable to what Hubble achieves in visible light, but it can see through environments that are completely opaque to Hubble. The telescope's sensitivity is enhanced by its location. Operating in space eliminates the absorbing effect of Earth's atmosphere, which blocks most infrared radiation from reaching the ground. And the telescope's position at the second Lagrange point on the opposite side of Earth from the Sun, combined with its enormous 5-layer sunshield the size of a tennis court, keeps the telescope's instruments at temperatures near -233 degrees Celsius, close to absolute zero. This is essential because any warm object emits infrared radiation, and a warm telescope would be blinded by its own thermal glow. By cooling its instruments to near absolute zero temperatures, James Webb maximizes its sensitivity to the faint infrared signals from distant objects. These engineering choices were not easy. The sunshield alone required years of development to design a structure that could unfold reliably in space. The mirror had to be built in segments that fold for launch and then deploy with micrometer precision. The entire telescope had to be designed to operate without any possibility of in-person maintenance, unlike Hubble, which was serviced multiple times by space shuttle crews. Everything had to work the first time, perfectly, more than 1 million kilometers from Earth. When the telescope successfully deployed all its components in January of 2022, and reached its operating temperature. The astronomical community collectively exhaled. The risk had paid off. The first full-color science images were released on July 12th of 2022, and they immediately demonstrated that the telescope was performing beyond its design specifications. The mirror alignment had been achieved with such precision that the images were sharper than theoretical models had predicted would be achievable. The sensitivity of the instruments was high enough to detect objects fainter than the mission requirements had specified. Every instrument on the telescope was functioning correctly. What followed has been a sustained period of scientific productivity, unlike any in the history of space astronomy. The telescope's observation schedule is managed by the Space Telescope Science Institute and is heavily oversubscribed. Far more scientists want to use it than it has time to accommodate. The programs it has conducted range from studies of planets and moons within our own solar system to observations of the very first galaxies in the universe, spanning more than 13 billion years of cosmic history in a single operational mission. The breadth of the telescope's scientific reach is one of its most remarkable characteristics. Unlike some missions, which are dedicated to answering a single question or studying a single class of objects, James Webb was designed to be a general-purpose observatory, capable of addressing almost any question in modern astrophysics. This generality has allowed it to produce breakthroughs in areas that were not its primary mission objectives. The discovery of exoplanet atmospheres is one example. When a planet passes in front of its host star as seen from James Webb, starlight filters through the planet's atmosphere before reaching the telescope. Different molecules in the atmosphere absorb specific infrared wavelengths, leaving characteristic dips in the spectrum of the transmitted light. By analyzing these spectral signatures, astronomers can determine which molecules are present in the planet's atmosphere, potentially including water vapor, carbon dioxide, methane, and other compounds that may be relevant to habitability, or even to the presence of biological activity. Prior to James Webb, such atmospheric characterization was possible only for the largest and hottest planets, gas giants orbiting very close to their stars. The telescope's sensitivity has extended this capability to smaller planets in cooler orbits, including some within the habitable zones of their host stars. Early results have already detected carbon dioxide in the atmosphere of a gas giant in another system, and have begun to characterize the atmospheres of smaller rocky worlds, though none has yet shown the complex chemical signatures that would suggest a biosphere. The telescope has also contributed to our understanding of the solar system's smaller bodies in ways that extend far beyond Centaur 29P, observations of Kuiper Belt. Objects have refined measurements of their sizes, shapes, and surface compositions. Studies of Jupiter's atmosphere have revealed details of cloud dynamics and chemical abundance patterns. Observations of Titan, Saturn's largest moon, have extended prior measurements of its atmospheric chemistry and surface features. And early observations of Uranus produced images showing a polar cap feature and ring structure in unprecedented detail. The sheer volume of data being produced creates its own challenge. 550 terabytes is not a figure that most people have intuitive sense of. To put it in perspective, a typical high-definition movie file is a few gigabytes. 550 terabytes is equivalent to approximately 150,000 high-definition movies. All of that data represents calibrated, scientifically useful observations, and analyzing it is a years-long process. Many of the telescope's early observations have not yet been fully analyzed. Papers are still being published based on data collected in the telescope's first operational year. The scientific return from its full operational lifetime will take decades to fully realize. This is not unusual in the history of space science. The Voyager missions, launched in 1977, are still generating scientific publications from their decades-old data. The archive of Hubble observations continues to yield discoveries made years or decades after the original exposures were taken. Scientific data does not expire. Every observation made by James Webb is permanently archived and available to researchers worldwide. Future scientists, using analytical tools not yet invented, will almost certainly find things in this data that current researchers cannot see. The telescope's longevity itself is an open question. The design lifetime of 10 years was based on the fuel needed for station-keeping maneuvers at the Lagrange point. The precision of the Ariane 5 rocket launch that placed the telescope on its trajectory required so little corrective fuel consumption that the actual reserves are considerably greater than the minimum needed to meet the design lifetime. Current estimates suggest the telescope may remain fully operational for 20 to 25 years, potentially into the mid-2040s. In that time, it will observe a wide range of transient events, follow up on discoveries made by other telescopes, study objects that have not yet been identified, and push its sensitivity to its physical limits. What will it find? The history of new telescopes suggests that the most important discoveries are usually the ones that no one predicted in advance. The cosmic microwave background, discovered accidentally by radio astronomers in 1965, revealed the thermal afterglow of the Big Bang. The accelerating expansion of the universe, detected in 1998 by teams studying distant supernovae, overturned a century of assumptions about cosmology. Pulsars, discovered serendipitously in 1967 by a graduate student who initially thought she had detected radio frequency interference, turned out to be rapidly rotating neutron stars whose properties enabled some of the most precise tests of general relativity ever performed. The pattern is consistent. New instruments that offer greater sensitivity or access to previously inaccessible wavelengths invariably discover things that existing theory did not predict. James Webb is the most powerful astronomical instrument ever constructed, operating in a wavelength range that has never before been accessible from space with this sensitivity and resolution. The probability that it will observe something that fundamentally changes our understanding of the universe is not a hope. Based on the history of astronomy, it is a near certainty. We are living through that process right now. The unexpectedly massive early galaxies are one manifestation of it. The anomalous supermassive black holes between merging galaxies are another. The interstellar comet's chemical composition is a third. The near confirmation of a planetary system around Alpha Centauri is a fourth. Each discovery builds on the others, not because they are directly connected by simple cause and effect, but because they each reveal a cosmos more complex, more active, and more varied than any single model can fully capture. The universe, it turns out, has had billions of years to work on its complexity. Every time we build an instrument capable of seeing a little more of it, we find more to see. This may be the most consistent finding in all of astronomy, not any specific discovery, but the pattern. The more carefully we look, the more there is. James Webb is looking more carefully than anything we have ever built, and it is going to keep looking, and we are going to keep being surprised for a long time to come. What we know with confidence is this: the universe is approximately 13.8 billion years old. In that time, it has produced hundreds of billions of galaxies, each containing hundreds of billions of stars, many with planetary systems. The physics that governs this structure operates consistently across scales ranging from the quantum to the cosmic, and we have been able to work out the basic principles of that physics through observation, an experiment conducted almost entirely from a single small planet over the course of a few centuries. That is an extraordinary achievement, and James Webb is its current frontier. The questions it will answer and the questions it will raise in the process of answering them will define the agenda of astronomy for decades. Some of the scientists who will analyze its final data sets have not yet been born. The discoveries they will make, building on what we are learning now, are entirely beyond prediction. That is not a limitation. That is what science is. Each answered question revealing a broader horizon. James Webb has given us a broader horizon than we have ever had before, and the exploration of that horizon has only just begun. The relationship between what we observe and what we understand is rarely straightforward. Observation precedes theory in some cases. Theory predicts observation in others. And the most interesting episodes in scientific history are usually the ones where the two come apart, where what we actually see refuses to conform to what our best theories say should be there. James Webb is generating a large number of these episodes simultaneously. The galaxy formation problem at the cosmic dawn is perhaps the most consequential of them. The standard cosmological model, lambda cold dark matter, is not a casual hypothesis. It is a framework that has been refined over decades using data from ground-based surveys, satellite experiments, particle physics, and theoretical computation. It accounts for the large-scale structure of the universe with impressive precision, the distribution of galaxies across billions of light-years, the temperature fluctuations in the cosmic microwave background radiation, the statistical properties of galaxy clusters, and many other observational phenomena are well described by this model. It works, in the sense that its predictions match observations across a wide range of scales and epochs. but it breaks down at the cosmic dawn. The galaxies that James Webb is finding in the first few 100 million years after the Big Bang are simply too numerous, too massive, and too structurally mature to fit within the model's predictions. If we accept the observations at face value, which the quality of James Webb's data requires us to do, then something about the way the early universe formed stars and assembled galaxies was fundamentally different from what the model describes. There are several ways to modify the model to accommodate these observations. One approach is to adjust the parameters that describe how efficiently gas collapses and forms stars in the early universe. If star formation efficiency was higher, galaxies could have assembled faster. The problem is that making this efficiency high enough to explain the observations requires values that conflict with other constraints from other observations. You cannot freely adjust one parameter in a tightly interconnected model without disturbing other things the model correctly predicts. Another approach involves the properties of dark matter itself, lambda. Cold dark matter assumes that dark matter consists of particles that were moving slowly at the time of the universe's formation, which is what makes it cold. Cold dark matter forms structure hierarchically, with small clumps forming first and then merging into progressively larger structures over time. This bottom-up assembly process produces a specific prediction for how quickly large structures like galaxies should have grown. If dark matter has different properties than the model assumes, the assembly timeline could be different. Warm dark matter, for instance, would produce a different pattern of early structure formation. But changing the dark matter model has its own consequences that must be checked against observations. The dark star hypothesis, discussed earlier, offers a different resolution that does not require modifying the fundamental cosmological framework. If the brightest sources that James Webb is observing in the early universe are not ordinary galaxies at all, but instead single enormous dark matter-powered stellar objects, then their luminosity and apparent mass would be dramatically misleading. A single very bright object with a mass measured in millions of solar masses would look, in a brief snapshot from 13 billion light-years away, like a galaxy. It would have the spectral signature expected for a massive young stellar population, but it would be a single object, not a collection of billions of stars. If dark stars are real and if some of them are massive enough, the early universe could produce a relatively small number of them that appear to James Webb's instruments as bright, compact, apparently massive early galaxies, resolving the discrepancy without requiring any revision to the underlying cosmological model. The catch is that there is not yet direct evidence that dark stars are real. They are a theoretical possibility, consistent with the known properties of dark matter and with general relativistic physics, but not confirmed by observation. James Webb may be capable of distinguishing between a dark star and an ordinary galaxy through spectroscopic analysis if their spectral signatures are sufficiently different. Researchers are currently working to determine what distinctive observational signatures dark stars would produce and whether any of the currently known early sources match those signatures. This kind of detective work, moving back and forth between theoretical predictions and observational data, is the core of astrophysics. It is slow and careful and requires checking every assumption at every step, but it is also progressive. Models that cannot account for new observations are revised or replaced. Observations that seem anomalous are scrutinized for systematic errors. When the anomalies survive scrutiny and the models cannot accommodate them, something new is learned. The scale of what James Webb is finding, across so many different areas simultaneously, suggests that we are in one of the more productive phases of that process. Multiple anomalies across multiple domains, multiple models under stress, multiple theoretical proposals competing for explanatory power. This is not a sign that science is failing. It is a sign that a new instrument of sufficient power has arrived to reveal what the previous generation of instruments could not show us. The history of astronomy is largely a history of this process. When Galileo first pointed a telescope at the sky in 1609, he discovered that the moon had mountains and craters, that Jupiter had moons of its own, that the Milky Way was composed of individual stars, and that the planet Venus showed phases like the moon, demonstrating that it orbited the sun rather than the Earth. Each of these observations had implications for the prevailing cosmological model of the time, and those implications were profoundly disruptive. The Earth was not the center of a perfect, unchanging celestial realm. The universe was not structured the way authoritative tradition insisted it was. The disruption, however, led to a better understanding. The model that emerged from the scientific revolution of the 16th and 17th centuries, the heliocentric solar system with its mathematical laws of planetary motion, described reality far more accurately than what it replaced. The temporary discomfort of having one's assumptions overturned is the price of progress. James Webb is applying a similar kind of pressure on current cosmological models, and the discomfort is scientifically productive. Researchers are working harder, thinking more carefully, and being forced to question assumptions that had become so deeply embedded in the standard framework that they were no longer being actively examined. What is the minimum star formation rate consistent with galaxy observations? What are the actual properties of dark matter at the scales relevant to early galaxy formation? Can primordial black holes form and survive in detectable numbers? What exactly drives the cryovolcanic activity of bodies like Centaur 29P? Each of these questions, sharpened by James Webb's observations, will generate years of theoretical and observational work. The planet formation discoveries are also generating new questions. The circumplanetary disk around CTHB is a rare and precious object, one of only a handful of such structures ever imaged. But it is almost certainly not unique. As James Webb continues to observe young stellar systems, it will image more of these moon-forming disks, and the comparison between them will reveal whether the carbon-rich chemistry found in CTHB is typical or unusual. If most young exoplanets are encircled by carbon-rich moon-forming material, the implications for the prevalence of organic chemistry across planetary systems are significant. If it is rare, understanding why would illuminate the specific conditions under which complex chemistry develops. The exoplanet atmosphere program at James Webb is similarly still in its early phase. The instruments have demonstrated the capability to detect specific molecules in planetary atmospheres, and the list of targets is being extended to smaller and cooler worlds with each observation cycle. The scientific community is cautiously watching for any combination of atmospheric gases that would be thermodynamically unstable unless continuously replenished by biological activity, what researchers call biosignatures. No such detection has been made, and expectations are appropriately measured. The technical challenge of detecting biology on a world light years away through the analysis of atmospheric spectra filtered through starlight is immense. But James Webb has the sensitivity to begin this search in a meaningful way, and the search is underway. The question of whether life exists elsewhere is the oldest and arguably the most consequential scientific question there is. James Webb will not answer it definitively, but it may narrow the field of candidates, identify the most promising targets for future missions, and detect the molecular building blocks of life in enough different environments to determine whether biology is a common or rare development in the universe. The interstellar chemistry revealed in Comet 3, I-Atlas, is relevant here. The detection of water vapor and carbon dioxide in high abundance in an object that formed in another star system, with the specific ratio that implies cold region condensation in that system's protoplanetary disk, is evidence that the chemical conditions for life are not peculiar to our solar system. The same molecular inventory that eventually, over 4 billion years on Earth, gave rise to living cells appears to be assembled elsewhere too. How often it gets far enough to produce life is a different question. But the first step, the availability of the raw materials, appears to be widespread. This is one of the recurring themes in what James Webb is finding. Universality. The processes that operate in our solar system operate elsewhere. The elements that make up our chemistry are distributed throughout the galaxy. The physics that governs star formation in our corner of the Milky Way operates on the far edge of the galaxy in a metal-poor environment 15,000 light-years away. The dynamics that assembled our own planetary system billions of years ago can be observed currently happening in real time in systems 600 light-years away. The universe does not appear to be doing anything specially configured for us. It appears to be running the same programs everywhere with the same basic code, producing variations in output that reflect local conditions, but not fundamental differences in the underlying rules. This universality, if confirmed across the broader dataset that James Webb is accumulating, would be one of the most significant scientific conclusions of the era. It would mean that our sample of one, our own solar system with its single inhabited planet, is not a bizarre anomaly, but a reasonable representative of a broad class of systems. It would mean that the conditions that produced us were not uniquely improbable, and by extension that they have likely been reproduced at least approximately, in a very large number of other places, across the galaxy and across the universe. Whether any of those other places have produced observers capable of asking these questions is something we cannot currently determine, but James Webb is providing the observational foundation on which the answer, whenever it comes, will be built. Let us return one final time to the question of what we do not know. We do not know the nature of dark matter. We do not know whether primordial black holes contributed to the universe's early structure. We do not know precisely how the first massive stars formed in metal-poor environments. We do not know whether dark stars are real. We do not know the detailed mechanism behind Centaur 29P's explosive outbursts. We do not know whether the planetary candidate around Alpha Centauri A has moons, or whether those moons might harbor liquid water. We do not know whether the early galaxies that are too massive and bright violate the standard cosmological model, or whether a revised model can accommodate them. These are not small questions. They are some of the biggest open problems in astrophysics, and James Webb is providing, for the first time, observational data with the quality needed to begin answering them. The telescope has roughly 2 decades of operational life remaining, 2 decades of observations at this sensitivity level, accumulating across but a vastly clearer one than any previous generation possessed. The universe is 4 dimensions of space and time, 13.8 billion years old, approximately 93 billion light-years across in the region we can observe, containing perhaps 2 trillion galaxies, each with hundreds of billions of stars, most with planetary systems, all governed by physics we have been working out for the last few centuries from a pale blue dot in an unremarkable corner of one of those 2 trillion galaxies. And yet here we are, looking out at all of it through golden eyes, asking why it is the way it is. That is the project. James Webb is its current best instrument, and the universe obligingly keeps surprising us. There is something worth pausing on in the sheer mechanics of how James Webb works that illuminates why its discoveries are so remarkable. The telescope's primary mirror is not one piece of glass. It is 18 individual hexagonal mirror segments, each 1.32 meters across, made of beryllium and coated with a film of gold approximately 100 nanometers thick. Gold was chosen not for aesthetics, but for function. It is among the best-known reflectors of infrared light, reflecting more than 98% of the infrared radiation that strikes it. The beryllium substrate was chosen because it is lightweight, dimensionally stable, and maintains its shape extremely well across the temperature range the telescope experiences. Each segment is individually adjustable using 7 actuators, tiny mechanical devices that can shift the segment's position by as little as 10 nanometers, roughly 1/100th the wavelength of visible light, to maintain precise alignment. That alignment process, conducted after the telescope reached its operating location, took approximately 3 months and required the careful coordination of the 18 segments to work together as a single optical surface. The result was a mirror that focuses infrared light with a precision that had never been achieved in space before. The quality of the alignment can be judged by looking at a James Webb image of a bright star. Instead of appearing as a simple point of light, the star is surrounded by a precise diffraction pattern, 6 long spikes arranged symmetrically. These spikes are not a flaw. They are a consequence of the mirror's geometry, the result of light diffracting around the edges of the hexagonal segments and the 3-strut secondary mirror support structure. The symmetry and sharpness of those spikes are a direct visual indicator of the quality of the alignment. A poorly aligned mirror would produce an asymmetric, blurry pattern. The pattern James Webb produces is textbook perfect. The telescope's instruments are located behind the primary mirror and include 4 main systems. The near-infrared camera, known as NIR-CAM, is the primary imaging instrument, covering wavelengths from 0.6 to 5 micrometers. The near-infrared spectrograph, called NIR-SPEC, can simultaneously measure the spectra of up to 100 objects in its field of view, allowing it to determine the redshifts, compositions, and properties of many galaxies or stars in a single observation. The mid-infrared instrument, known as MIRI, covers longer wavelengths from 5 to 28 micrometers and includes both an imager and a spectrograph, and the fine guidance sensor and near-infrared imager and slitless spectrograph, a dual-purpose instrument used both for precise pointing control and for additional spectroscopic observations. The combination of these instruments makes the telescope capable of studying almost any type of astronomical object across a broad range of physical conditions. Young stars and planetary disks require different wavelengths and different techniques than ancient distant galaxies. Comets in the outer solar system have different spectral characteristics than exoplanet atmospheres. James Webb can do all of these observations, sometimes switching between targets and modes within the same observation period. The scheduling of these observations is itself a complex undertaking. The telescope can only point in certain directions depending on its orbital position and the position of the Sun relative to the telescope's sunshield. Some targets are only accessible during certain periods of the year as the telescope orbits around the Sun with Earth. High-priority targets that require specific timing, such as transits of exoplanets, must be scheduled precisely. Competing demands for telescope time are evaluated by independent scientific review committees. The selection process for which programs receive observing time is competitive, with many times more proposals submitted than can be accommodated. The resulting observation schedule represents a scientific judgment about which questions are most important and most tractable given the telescope's capabilities. And the return on that investment has been evident in the breadth and significance of the discoveries already made. What does it feel like as a scientist to receive data from an instrument like this? The data arrives in digital form, transmitted to Earth via radio, and processed through a pipeline that applies calibration corrections, removes instrumental artifacts, and produces cleaned images and spectra. A typical science program might wait months between submitting the proposal and receiving the data, then spend months more analyzing it. The analysis involves specialized software, statistical methods, comparison with theoretical models, and extensive cross-checking. A paper describing the results is written, reviewed by other scientists before submission, submitted to a scientific journal, reviewed again by independent experts in a process called peer review, revised in response to reviewer comments, and eventually published. The entire process from observation to publication commonly takes 1 to 3 years. But despite this slow and careful process, the significance of what the data contains is often apparent very early. When the team analyzing the Alpha Centauri system detected that faint point of light next to the star, they would have known within hours of processing the image that they might be looking at the first directly imaged planet in the nearest stellar system to our own. Verifying that conclusion, ruling out alternative explanations, and characterizing the object in detail takes much longer. But the initial recognition of discovery is immediate. This is why James Webb's images resonate so broadly beyond the scientific community. They are not just technically impressive. They are evidence that we have genuinely extended the reach of human perception into regions of space and time that were previously inaccessible. When we look at an image of a galaxy that existed 300 million years after the Big Bang, we are not just seeing a picture. We are looking at a part of the universe's history that no living thing, to the best of our knowledge, has ever directly observed. The light in that image has been traveling through space for approximately 13.5 billion years. It left its source before the Earth existed, before our Sun existed, before any of the stars in our local neighborhood existed, and it ended its journey in the detectors of a telescope that a species of mammals built on a planet that formed 4.5 billion years ago from the recycled remnants of older, dead stars. There is something profound in that chain of causation. The carbon in our bodies was made in the cores of stars that exploded billions of years ago. The same stellar explosions that carved those bubble-shaped cavities in the Phantom Galaxy, visible in James Webb's infrared images, spread the heavy elements that eventually, through further cycles of stellar birth and death, became the material of our solar system, our planet, and ultimately us. When we observe the universe with James Webb, we are, in a very literal sense, matter that has organized itself sufficiently to observe its own origins. The telescope is not just a scientific instrument, it is an expression of a capacity that, as far as we know, is rare in the universe. The capacity to look back at the cosmos and ask how all of this came to be, whether that capacity is unique to life on Earth or is distributed throughout the universe among many. Technological civilizations is a question that James Webb may help address indirectly, by determining how common the conditions for biology are, and directly, by listening for or observing any signatures of technology elsewhere. No such signatures have been detected by James Webb or by any other instrument. But the search continues. and the tools for conducting it are improving. What we can say with confidence is that the universe is very old, very large, and very busy. It has been forming stars, assembling planets, evolving chemistry, and building structure for nearly 14 billion years. The processes James Webb is observing today, the bipolar jets of a forming protostar, the crystalline ice gradually releasing its trapped gases in the interior of an ancient comet, the collision of two galaxies in the early universe, the slow accumulation of mass in a young planetary system, these are not anomalies. They are the ordinary, ongoing business of a universe that has been running similar programs for most of its history. We just happen to be watching at a particular moment, with a particular instrument that is powerful enough to see more clearly than anything that came before it. The window is open, the view is extraordinary, and the exploration has only just begun. Understanding where we came from requires understanding how everything around us formed. James Webb is answering that question layer by layer, scale by scale. From the organic molecules trapped in cometary ice at the edge of our solar system to the first flickering of galactic light at the edge of the observable universe. Each measurement adds to a picture that no previous generation of scientists could have assembled. The picture is not complete. It may never be complete. The universe is under no obligation to be fully comprehensible to the beings it has produced. But it is more complete than it was 3 years ago, and it will be more complete still in another 3 years. And another 3 after that. As long as this extraordinary instrument continues to point its golden eye at the dark, that is enough. That is, in fact, remarkable. If you have followed this journey from Neptune's rings to the edge of the observable universe, from ice volcanoes on an ancient comet, to the question of whether invisible primordial black holes might be threaded through the space between galaxies, you already understand why this telescope matters. Not just for science, for us, for everything we want to know about what kind of universe we have been born into, what it is made of, how it began, how it evolved, and what it might yet reveal. The answers are coming. James Webb is finding them, and the universe, for all its vast indifference, is cooperating beautifully. The deepest discoveries often emerge not from a single dramatic observation, but from the accumulation of many careful measurements that gradually reveal a pattern no single data point could disclose. James Webb's contribution to our understanding of galaxy evolution is a perfect example of this principle at work. When astronomers talk about galaxy evolution, they are describing one of the most sweeping processes in all of science, the transformation, over billions of years, of the initial conditions after the Big Bang into the structured, diverse array of galaxies we observe today. Every spiral galaxy, every elliptical galaxy, every irregular dwarf galaxy is the product of this process. Our own Milky Way, with its central bar and sweeping spiral arms containing hundreds of billions of stars, is itself a middle-aged product of this process, assembled over the last 10 to 12 billion years through a combination of slow in-situ star formation and the merger of smaller galaxies. The standard picture of galaxy formation goes roughly as follows. In the early universe, dark matter collapsed under its own gravity into structures called halos. Gas fell into these halos, cooled, and began forming stars. The first stars were massive and short-lived, burning through their fuel in millions rather than billions of years, and exploding as supernovae that seeded the surrounding gas with the first heavy elements. Successive generations of stars formed from this progressively enriched gas, building up the stellar populations of early galaxies. Small galaxies merged to form larger ones. Gas continued to accrete from the surrounding cosmic web, fueling additional star formation. And the feedback processes, the energy and momentum deposited into the gas by supernovae, stellar winds, and the radiation of massive stars, regulated the rate at which gas could cool and form stars, preventing galaxies from converting all their gas into stars too quickly. This picture is well supported by observations of the universe at moderate distances, corresponding to cosmic epochs between a few billion and 10 or so billion years after the Big Bang. Galaxy surveys conducted with ground-based telescopes and with Hubble have mapped the distribution and properties of hundreds of thousands of galaxies across this range of distances, and the data largely conform to the theoretical framework. The challenge has always been the earliest epochs, before a few 100 million years had elapsed, where previous telescopes lacked the sensitivity to observe with any statistical precision. James Webb is filling this gap, and the data are telling a story that does not entirely match the theoretical framework. The discrepancy is not just in the existence of a few unexpectedly massive early galaxies. It is in the statistical distribution of galaxy properties at early times. The number density of bright massive galaxies in the first billion years of the universe is higher than models predict. The star formation rates inferred for some of these early systems are extreme, far higher than what the standard theory says should be possible given the available gas and the expected feedback processes. And some of these galaxies appear to be already shutting down their star formation, transitioning to the passive red dead state that is more characteristic of massive galaxies in the local universe, in a timescale that seems too short to be easily accommodated within standard models. Each of these anomalies individually might be explained away: a statistical fluctuation, an observational bias, an underestimate of measurement uncertainties. But the accumulation of multiple anomalies pointing in the same direction is harder to dismiss. The early universe appears to have been more efficient at building massive galaxies than theoretical models of galaxy formation predict. Something in the physics of early star formation, early feedback, or early dark matter behavior is not captured correctly in current models. This does not mean the standard cosmological model is wrong in its broad strokes. It means the details of how gas cools, collapses, forms stars, and responds to feedback in the extreme conditions of the very early universe need to be better understood and better modeled. This is an active area of theoretical astrophysics, and the James Webb data are driving enormous productivity in that area as theorists work to build models capable of reproducing what the telescope is finding. One productive approach involves what researchers call high redshift galaxy simulations, computational models that attempt to simulate the formation and evolution of galaxies from just after the Big Bang through the epoch that James Webb is now observing. These simulations require enormous computing resources, running on supercomputers for weeks or months to model regions of the universe that span hundreds of millions of light years across cosmic time. The best current simulations produce galaxies whose statistical properties broadly match observations at intermediate distances. The challenge is extending their validity into the regime that James Webb is now probing, where the physics of very early, very dense, very hot environments may require additional physical processes not included in current simulation frameworks. Some theorists have proposed that the resolution lies in variations in the efficiency of stellar feedback. If the first generation of massive stars in early galaxies was particularly effective at compressing and shocking the surrounding gas, rather than simply heating and dispersing it, this could have triggered additional star formation rather than suppressing it, producing brief periods of extraordinarily rapid stellar growth. These starbursts, if sufficiently intense, could explain the luminosities and stellar masses that James Webb is observing without requiring a wholesale revision of the cosmological framework. Others have proposed modifications to how we model the interaction between the radiation of young massive stars and the surrounding gas. The ionizing photons produced by the earliest, hottest stars could have escaped their host galaxies more easily than simulations currently assume, reducing the amount of feedback within the galaxy and allowing star formation to proceed more rapidly. This escape fraction of ionizing photons is also relevant to understanding how the universe transitioned from being neutral in the aftermath of the Big Bang to being fully ionized as it is today, in the process known as cosmic reionization. James Webb is measuring this escape fraction in early galaxies directly for the first time, and the values it is finding are crucial input for both the galaxy formation models and the reionization models. The intersection of these different areas of inquiry is one of the things that makes early universe astronomy so rich. The questions are connected. How efficiently early galaxies formed stars affects how quickly they could ionize the surrounding intergalactic medium. The ionization state of the intergalactic medium affects how gas is able to flow into galaxies to fuel further star formation. The properties of the first black holes affect how much energy they deposited into their host galaxies and the surrounding gas. And all of these processes depend on the underlying dark matter structure, which sets the gravitational framework within which everything else unfolds. James Webb is providing observational constraints on all of these processes simultaneously. It is measuring star formation rates, galaxy masses, black hole masses, gas compositions, ionizing photon escape fractions, and intergalactic medium properties across the epoch of cosmic reionization. No previous telescope could do this. The combination of infrared sensitivity, spectroscopic capability, and spatial resolution that James Webb provides is uniquely suited to this era of cosmic history. The results so far have confirmed that reionization was patchy, proceeding at different rates in different regions of the early universe as the first galaxies lit up and their radiation carved ionized bubbles in the surrounding neutral gas. They have confirmed that massive early galaxies contributed significantly to this reionization, though the precise balance between the contributions of different galaxy types is still being worked out. And they have raised new questions about the timing and efficiency of the process that will require many more observations to resolve. Beyond the first galaxies, James Webb is also transforming our understanding of what happens when galaxies interact and merge. Galaxy collisions are not rare events in the universe's history. Galaxies in groups and clusters interact gravitationally, tidally distorting each other, stripping gas from outer regions, and sometimes merging into larger structures. The Milky Way itself bears the gravitational scars of past interactions and will eventually merge with the Andromeda Galaxy in roughly 4.5 billion years, a collision that will fundamentally restructure both galaxies over the course of 1 billion years or so. When James Webb observes interacting galaxy systems in the early universe, it can study the effects of these collisions on star formation, gas distribution, and black hole activity at a level of detail that was not previously possible. The observation of two merging disk galaxies with an anomalous supermassive black hole in the space between them, discussed earlier, is one example of the unexpected discoveries that come from looking at these systems with new eyes. But there are many more. James Webb has observed galaxy pairs showing evidence of enhanced star formation triggered by the gravitational compression of gas during the interaction. Extended streams of stars and gas pulled out by tidal forces during close passages, and the signatures of gas being channeled toward the centers of galaxies where it can fuel black hole growth. Each of these observations contributes to a more detailed understanding of how the merger-driven component of galaxy evolution operates and how it interacts with the slower in situ processes of gas accretion and internal star formation. Over the decades of James Webb's operational lifetime, the statistical sample of interacting and merging systems will grow large enough to draw robust conclusions about how mergers shape the properties of the resulting galaxies across a broad range of masses, redshifts, and environments. The telescope is also revealing details of the circumgalactic medium, the diffuse gas that surrounds galaxies, and serves as the reservoir from which they draw fuel for star formation and into which they expel gas through supernova winds and black hole feedback. This medium is enormously extended, stretching out to distances comparable to the separation between galaxies in a group, and its properties determine how long a galaxy can sustain star formation and how it responds to environmental influences. Previous observations of this medium were limited by sensitivity. James Webb is beginning to map its properties in emission and absorption with sufficient precision to start testing models of how gas cycles in and out of galaxies across cosmic time. What all of these observations have in common is that they are addressing questions that are not new. Astronomers have been asking how galaxies form and evolve since the middle of the 20th century. But the quality of the data available to answer these questions has been, until now, insufficient to distinguish between competing models. James Webb is, for the first time, providing data precise enough to make those distinctions. Some models will be confirmed, others will be ruled out, and the resulting reduction in theoretical uncertainty will represent genuine progress in our understanding of how the universe works. The same pattern of long-standing questions finally approaching resolution applies across the full range of topics that James Webb is addressing: the mechanisms of planet formation, the chemistry of planetary atmospheres, the nature of the earliest cosmic objects, the properties of dark matter, the origin of supermassive black holes. In each of these areas, there is a theoretical framework that has been refined over years or decades, and that is now being tested against James Webb data with a precision that was not previously achievable. In some cases, the data will confirm the existing framework and allow it to be refined further. In other cases, the data will reveal anomalies significant enough to require revisions. And in at least some cases, the data will reveal something so unexpected that it genuinely opens a new research direction that no existing framework had anticipated. We are already seeing all three types of outcome in the early results. The confirmation of the core accretion model of massive star formation from the Sharpless 2284 observations is an example of the first type. The unexpectedly mature early galaxies are an example of the second. The anomalous supermassive black hole between the two merging disk galaxies is arguably an example of the third, a discovery that fits no clear existing framework and will require new theoretical work to explain. This three-way distribution of outcomes is exactly what you would expect from an instrument operating at a new sensitivity frontier. It is a healthy and productive scientific situation, even if it sometimes generates the temporary discomfort of having familiar assumptions challenged. The discomfort is temporary. The progress is permanent. That is the long view of what is happening right now with James Webb. Not just individual discoveries, however striking, but the systematic expansion of the empirical foundation on which our understanding of the cosmos rests. Each observation is one more constraint on the space of possible universes, narrowing the range of theories that are consistent with what we actually find and guiding the development of better models. This is slow work. It is meticulous work. It requires the sustained effort of hundreds of scientists, engineers, programmers, and administrators working across multiple countries and institutions. But it is also work that is cumulative in a way that few human endeavors are. Every measurement made by James Webb becomes a permanent part of the scientific record. Every constraint it provides on galaxy formation, planet formation, or black hole physics is a constraint that will still be valid and useful 50 years from now. The archive grows with every observation, and it will be mined for discoveries long after the telescope itself has fallen silent. This permanence is one of the underappreciated aspects of science as a human practice. The knowledge it produces, when honestly and carefully obtained, does not expire. The wavelengths of light absorbed by specific molecules in a planetary atmosphere do not change. The relationship between a galaxy's redshift and its distance, measured by James Webb with high precision, is real data about the real universe that will remain valid regardless of what subsequent theories say. The measurements accumulate, the constraints tighten, and understanding advances, generation after generation. We are adding to that accumulation right now, with the most powerful observatory ever aimed at the sky. And while we cannot fully see where the path leads, the direction is clear, toward a more complete and more accurate understanding of the universe we inhabit, one observation at a time. That is the project. That is what James Webb is doing. And it is by any measure extraordinary. Returning to one of the most immediate and tangible discoveries James Webb has made, it is worth spending more time on what the telescope's observations of planetary systems are teaching us about our own origins. Our solar system formed approximately 4.6 billion years ago from a collapsing molecular cloud of gas and dust. That collapse, triggered perhaps by a nearby supernova, whose shockwave compressed the cloud past the threshold for gravitational instability, produced a rotating disk of material around the newborn sun. Over the next several million years, that disk condensed and organized. Dust grains collided and stuck together, gradually building up into centimeter-sized aggregates, then meter-sized boulders, then kilometer-sized planetesimals, then larger planetary embryos, and eventually the 8 planets we know today, along with the population of smaller bodies, the asteroids, comets, and Kuiper belt objects that represent the leftovers from that formative process. We know this story in broad outline, but the details have always been difficult to constrain directly because we have only one complete example to study, our own solar system. And by the time we arrived to observe it, the formative process was 4.5 billion years in the past. The disk was gone. The planetesimals had either been incorporated into planets or ejected. The early dynamics had been overwritten by billions of years of subsequent evolution. We could infer what happened from the current configuration of planets and from the chemical and isotopic composition of meteorites, but we could not watch it happen. James Webb can watch it happen elsewhere, in other systems, at various stages of their formation. And by comparing what we observe in systems of different ages, we can construct a more detailed and empirically grounded picture of how planetary systems assemble. The CTHB system, with its circumplanetary disk of carbon-rich organics around a young giant planet, is a window into the moon formation phase of a giant planet's early life. The contrast in chemistry between the planet's moon-forming disk and the star's planet-forming disk, The abundance of carbon in one and its relative scarcity in the other tells us something about the chemical differentiation that occurs as material organizes within a protoplanetary system. Similar differentiation may have occurred in the early solar system, potentially explaining some of the differences we observe today between the rocky, inner planets and the ice-rich outer solar system. The Pillars of Creation observations give us a direct view of stellar birth and early protoplanetary disk formation. The newly forming stars visible in James Webb's infrared images are at a stage only a few 100,000 years past their initial collapse, before any planets have formed and before the disk has had time to organize into the rings and gaps that later emerge as the precursors of planetary orbits. Studying these very early systems allows us to understand the initial conditions from which planetary systems develop, the mass of the disk, its temperature structure, its chemical composition, and how the nascent star's radiation is already beginning to influence the disk material. At intermediate ages, James Webb is revealing the diversity of planetary system architectures. Some young systems show disks with prominent ring structures and cleared gaps, evidence of planets already forming and gravitationally sculpting the disk material. Others show more uniform disk structures, suggesting a different stage of development or different physical conditions. The diversity in disk structures mirrors the diversity in planetary system architectures we observe in mature systems, and understanding the connection between the two will be one of the telescope's long-term contributions to planetary science. The detection of molecules in these disks, water, carbon dioxide, hydrocarbons, and more complex organic species, is particularly important because these molecules are the precursors of planetary chemistry. The water in a planet's ocean must come from somewhere. The organic molecules in the interstellar medium and in protoplanetary disks are the starting material from which eventually the complex biochemistry of life is assembled. By mapping the distribution and abundance of these molecules in forming planetary systems, James Webb is documenting the initial chemical inventory available for planet formation and, potentially, for the emergence of biology. The interstellar comet discovery reinforces this picture from a different angle. Comet 3. I-Atlas, arriving from another star system with a high ratio of carbon dioxide to water vapor, demonstrates that the molecular inventory of our solar system is not unique. Another star system, unknown distance away, in an unknown direction, produced a disk with cold regions where carbon dioxide ice condensed, and eventually produced a body that ended up being ejected from that system and making a long journey through the interstellar medium before entering ours. The chemistry it carries is direct evidence of the conditions in that other system's planet-forming disk. This is a new kind of astronomy, reading the chemistry of distant planetary systems not by observing them directly, which is extraordinarily difficult for all but the most nearby systems, but by intercepting their cast-off material as it drifts through the galaxy. Each interstellar visitor that enters the solar system is a message from its home system, and James Webb is now sophisticated enough to read those messages in detail. The galactic context for all of this planetary and stellar science is important. The Milky Way contains somewhere between 100 billion and 400 billion stars. The true number is uncertain, because the dust that James Webb is designed to see through also obscures our view of the galaxy's center, where star density is highest. Current estimates of the total stellar population, based on infrared surveys and dynamical models, favor numbers in the range of 200 to 300 billion stars. If even a fraction of these stars host planetary systems, and all evidence suggests that planetary systems are common rather than rare, then the number of planets in the Milky Way is enormous. Estimates range from hundreds of billions to trillions, with the uncertainty driven by the fraction of low-mass stars that host multiple planets rather than the question of whether planetary formation occurs at all. Among those trillions of planets are, with near certainty, many that are rocky in the size range of Earth, and in the habitable zones of their host stars where liquid water could exist on the surface. The question of how many of those potentially habitable planets are actually inhabited, and whether any of that life has evolved to technological complexity, is one that science cannot currently answer. What we can say is that the building blocks are common. Water is the second most abundant compound in the universe after molecular hydrogen. Carbon, the backbone of biochemistry, is the fourth most abundant element in the cosmos. Organic chemistry, the chemistry of carbon-containing compounds, occurs naturally throughout the interstellar medium, in comets, in asteroids, and on the moons of giant planets in our own solar system. The conditions required for life, or at least for the chemistry from which life can emerge, appear to be widespread. Whether widespread conditions for life's chemistry translate into widespread life, and whether widespread simple life translates into widespread complex life and technological civilization, are the deeper questions that we cannot currently constrain well. But James Webb is beginning to provide data relevant to those questions, in the form of atmospheric characterization of potentially habitable worlds and in the detailed mapping of organic chemistry and planetary formation. Environments. The telescope will not answer the question of whether we are alone, but it will provide, over its operational lifetime, a much richer picture of the astronomical context within which that question must be answered. And that picture, in its detail and breadth, will be one of the lasting contributions of this remarkable instrument. There is one more thread worth following before we step back to the wide view. The cosmic microwave background is the oldest light in the observable universe. It was emitted approximately 380,000 years after the Big Bang, when the universe first cooled enough for electrons and protons to combine into neutral hydrogen atoms, making the previously opaque plasma suddenly transparent. This light, released in every direction simultaneously across the entire observable universe, has been traveling ever since, stretched by cosmic expansion from the wavelengths of visible light into the microwave range. It arrives at Earth from every direction in the sky with almost perfectly uniform intensity, differing by only 1 part in 100,000 across the full sky. Those tiny temperature variations, measured with extraordinary precision by satellite experiments, encode the density fluctuations of the early universe, the seeds from which all cosmic structure, including every galaxy James Webb has ever observed, eventually grew. The pattern of these fluctuations is consistent with the predictions of inflationary cosmology, the theory that the universe underwent an extraordinarily rapid expansion in a brief interval immediately after the Big Bang, smoothing out any larger scale structure and generating the quantum fluctuations that became the seeds of structure we see. Today, James Webb cannot observe the cosmic microwave background directly because it operates at infrared wavelengths shorter than microwave, but its observations of the large-scale structure of the universe at high redshifts are complementary to cosmic microwave background measurements and can be used to test and refine the cosmological model that both sets of observations are probing, the tension between different measurements of the universe's current expansion rate. The Hubble constant discrepancy mentioned earlier in the context of the gravitational lensing observations is relevant here. Measurements of the expansion rate derived from the cosmic microwave background and from the standard cosmological model give a value that is consistently slightly lower than measurements derived from observations of nearby galaxies and standard candles. This tension has persisted for years and has not been resolved despite extensive efforts to find systematic errors in one or both sets of measurements. If the tension is real, it implies that there is something wrong with the standard cosmological model, either in the nature of dark energy, the nature of dark matter, or some other aspect of the physics that governs the universe's expansion history. James Webb is contributing to this question through multiple avenues. Its observations of supernovae in distant galaxies provide additional distance measurements that constrain the expansion history. Its gravitational lensing time delay measurements provide independent constraints on the expansion rate at intermediate distances. And its surveys of early galaxies provide input for cosmological models that connect the early universe, as measured by the cosmic microwave background, to the late universe, as measured by galaxy surveys and standard candle observations. Whether James Webb will resolve the Hubble tension or deepen it is not yet clear. What is clear is that its contribution to this question will be significant, and that the answer, when it comes, will have implications for our understanding of the universe that extend far beyond any single observation or discovery. This is the nature of fundamental science. The threads are all connected. The questions are all related. What we learn about galaxy formation tells us something about the nature of dark matter. What we learn about dark matter tells us something about the universe's expansion history. What we learn about the expansion history tells us something about the conditions at the Big Bang. And what we learn about the Big Bang, about those first moments of extreme density and temperature, tells us something about the physics that governs everything that has happened since, including the formation of every star, every planet, And every living thing, James Webb sits at the intersection of all of these threads. It is not the only instrument contributing to any of these questions, but it is uniquely positioned to contribute to all of them simultaneously, with a sensitivity and resolution that makes its contributions particularly valuable. The scientific community recognized this when it fought for decades, through multiple rounds of budget challenges and technical setbacks, to see the telescope built and launched. The return on that investment, already evident in the first few years of operation, will continue to compound for as long as the telescope remains operational, and the data it has collected continues to be analyzed. We are living through a genuinely special period in the history of our species. Attempt to understand the cosmos. Future generations will look back on this era the way we look back on the age of Galileo or the age of Einstein, as a time when the tools available to science made a leap that fundamentally changed what questions could be asked and answered. James Webb is the central instrument of that leap, and the discoveries it is making, from the ice volcanoes of a comet in our own solar system to the primordial galaxies at the edge of the observable universe, will be remembered as among the most significant achievements of our time. The sky has never been so clearly seen, and what it reveals in all its strangeness and grandeur and complexity is more than we dared to expect. More always is. To fully appreciate where James Webb sits in the arc of astronomical history, it helps to trace the sequence of instruments that preceded it and what each one revealed about the limits of the previous generation's understanding. Before any telescope existed, humanity's knowledge of the cosmos was derived entirely from the naked eye. The ancient Greeks mapped the visible stars, tracked the wandering of the planets, and developed sophisticated geometric models to describe the motions of the celestial bodies. Hipparchus produced a star catalogue in the 2nd century before the Common Era. Ptolemy refined the geocentric model of the solar system into a system of epicycles that made reasonably accurate predictions of planetary positions. These were genuine achievements of careful observation and systematic reasoning. But the universe visible to the naked eye is a small fraction of what actually exists. The most distant object visible without optical aid is the Andromeda Galaxy, roughly 2.5 million light-years away, and even that appears only as a faint smudge to the unaided eye on the clearest nights. Everything beyond it was invisible. Galileo's telescope changed this in 1609. Within months of first pointing a telescope at the sky, he had discovered the 4 largest moons of Jupiter, observed the phases of Venus, resolved the Milky Way into individual stars, and mapped the mountains and craters of the moon. These observations alone were enough to overturn centuries of philosophical and theological certainty about the structure of the cosmos. The Earth was not the immovable center of a perfect heavenly sphere. It was one world among many, moving through space like the others. Over the following centuries, telescopes grew larger and more sophisticated. The development of spectroscopy in the 19th century added a new dimension to astronomical observation, allowing astronomers to determine the chemical composition of stars and nebulae from the pattern of dark lines in their spectra. The discovery in the early 20th century that the Milky Way was one of many galaxies, by Edwin Hubble's measurements of Cepheid variable stars in what was then called the Andromeda Nebula, extended the known scale of the universe by orders of magnitude, and Hubble's subsequent discovery that distant galaxies were receding from us at speeds proportional to their distances, the observational foundation of the expanding universe, opened the question of what the universe looked like in the past, and whether it had a beginning. The answer came in stages. The cosmic microwave background, discovered in 1965, confirmed that the universe had emerged from a hot, dense, early state and had been expanding and cooling ever since. The development of the lambda cold dark matter cosmological model in the 1980s and 90s provided a quantitative framework that correctly predicted the large-scale structure of the universe, the distribution of galaxies, galaxy clusters, and the cosmic web of filaments and voids, and the discovery of the universe's accelerating expansion in 1998, attributed to the dark energy that constitutes roughly 68% of the universe's total energy content, completed the basic inventory of cosmic components, ordinary matter, and dark energy, in a universe that has been expanding for 13.8 billion years. This framework is remarkable in its explanatory power, but it rests on observations that, until James Webb, were limited in their ability to probe the earliest epochs of the universe's history. The predictions of the model for what the first galaxies should look like how massive they should be, how quickly they should have formed, were based on theoretical extrapolations of processes observed at later times. James Webb is the first instrument capable of directly testing those predictions, and it is finding that they need refinement. This does not invalidate the broader framework, or it refines it. And the process of refinement, driven by new observations, is how science progresses. Each cycle of observation and model revision increases the precision and completeness of our understanding, asymptotically approaching a more accurate picture of reality. What is unusual about the current moment is the rate at which new constraints are being provided. James Webb is generating more high-quality constraints on the early universe in a few years than all previous instruments combined produced over decades. This acceleration of empirical input to theoretical astrophysics is pushing the field forward at an unprecedented pace and will continue to do so for as long as the telescope operates. The scientists working in this field are not lost in uncertainty. They have a solid framework, robust observations, and powerful computational tools. They also have James Webb, telling them with increasing clarity what the universe actually did in its earliest moments. And the conversation between what the universe did and what the models say it should have done is the most productive scientific conversation in modern astrophysics. That conversation is ongoing. It will not conclude in a single paper or a single discovery. It will proceed, question by question and observation by observation, for as long as scientists continue to ask what the universe is, where it came from, and what it might yet reveal. James Webb has made that conversation richer, sharper, and more exciting than it has been in many years. And that, ultimately, is the measure of a truly great scientific instrument.